I know, I'm sorry. All right,
Yeah,
so let's see.
It's recording.
Okay, great. So welcome everybody to this calculus workshop session. It's a session on integration applications. And this is in for Long Night Against Procrastination put on by the ALC. And we're going to look at 4 specific problems dealing with one with area, 2 with volume, and 1 with arc length. And each of those are applications of the integral. Okay, so let's get started with this area problem. It says sketch the region bounded by the graphs of y equals 9 minus x squared and y equals x plus 3 and find the area of the bounded region. Okay, so sketch the region, find the area bounded by the region. Okay. I think that since it's very short, we can just go ahead and I'm just going to put number 16 right here and then just get started with that. Well, maybe I should clip it, huh? I think I am going to clip. Sorry, guys.
No, do whatever you got to do.
Now that I feel like I'm rushing now. I don't want to do that. Okay. All right. So, all right. The first thing we're going to do is we are going to sketch this region. It's a parabola and a line, so this should not be too difficult. You guys should absolutely be able to do this. First, it doesn't give us any bounds, so we're assuming that where they intersect, because it's the area between these two graphs. So we're going to find the intersecting points, and that'll be the bounds of our integral. Okay, so let's do that first. Let's put 9 minus x squared equal to x plus 3. This is how you find your intersecting points. And looks like this factors very nicely. So I get x equals negative 3 and x equals positive 2. If I plug in negative 3, I'll get the point negative 3, 0. And I'll get the point 2, 5. Okay. So let's go ahead now and graph, since I have these points here. So negative 3, 0. And 2, 5. So the line, I see it goes, the y-intercept is 3. Okay, so there's the line. Let's draw the parabola. Sorry about that. Now I'm drawing the parabola in green. The parabola's vertex is at 9, so that's why I went up to 9 on the y-axis. It's this downward parabola here. And it looks like my top function, see, I have to graph it to know my top function. My top function is the parabola, and the bottom function is the line. Now, whenever you're sketching, you should always shade, because it is an area. So sometimes I see students, not shading, and it's just, well, you should. So there's my shading. What's that?
Yeah, you should. Yes.
Yes, you should. It's an area. So sketch the region, okay, or the area of the region. Okay, so let's put a rectangle, and looks like I'm going to use a vertical rectangle, delta x. And anywhere, I'm always looking, anywhere I put this rectangle in this area, it's going to travel from negative 3 to 2. So as it's traveling, as we're summing, I'm making sure that the rectangle always touches the top function, which is the parabola, and it does, and always touches the bottom function, as it's traveling sideways from negative 3 to 2. That's how your integration is working. So this is a good, I'm going to use one integral. Let's go ahead. Maybe let's change colors. Let's do it in purple or something. All right, so my area is the integral from a to b, the top function f of x minus the bottom function g of x dx. So my area is the integral from -3 to 2 of negative x squared, what was it, plus 9, minus x plus 3 dx. So if I distribute the minus sign, combine like terms, I get negative x squared minus x plus 6 dx. Integrating that, I get negative x cubed over 3 minus x squared over 2 plus 6 times x from -3 to 2. So I get negative 2 cubed over 3 minus 2 squared over 2 plus 6 times 2 minus -3 quantity cubed over 3 minus -3 quantity squared over 2 plus 6 times -3. So what is this? -8 cubed minus 2 plus 12. All right, let's think about this. Minus 27 with another minus in front makes it plus, and then the other minus makes it minus 27 thirds, which is actually 9. And then there'll be a plus 9 halves minus plus 18. You guys check my math here. So I have -8 thirds plus 9 halves. Should be 28, huh? Is that what this is? 30 minus 2 is 28. All right, so I think I messed up. It's not 28. You forgot to
subtract the 9.
I know, I forgot to subtract 9. 29 minus 8, 21, right? All right, so now let's do, and your calculator would do this for you if you do that. I just like to do it the old-fashioned way. So I get 16 over 6, 2 goes 3 times 27 over 6, and 21 times 6 is what? 126.
19 instead of 21.
Yeah. Did I do something wrong? 137? That's not what I have on my paper. Did I make a mistake? 3 goes into 6.
You've subtracted wrong. It's not 21, it's 19.
Did I? Yeah. I don't know what I did. Okay. 19. Thank you. So this makes this, all right, 19 times 6. 114. Oops. And that's what I have in my calculator, 120. I mean, that's what I have on my paper. I'll work these ahead of time, but I don't know if they're right or not. So, all right, you guys already caught a mistake I had made that I didn't make on my paper, but here we go. I have 125 over 6. Everybody agree?
Yes, yes, yes.
Any questions about it? It's pretty straightforward. Remember, just some things to note, area cannot be negative. So you must get a positive. You could do everything correctly except swapping the f minus g. If you have g minus f, that'll give you negative 125 over 6. If you swap your, if you put 2 to -3, that'll make your answer negative 125 over 6. So several things like that, besides a calculation error, you know, that'll get you a wrong answer. But so be careful with graph it, and then you'll know what's top and bottom. All right, any other questions? Okay, Dave, you want to do number?
I have the graph of that one too.
Okay.
We have time for it.
Yeah, I think. Oh.
I was trying to get my volume of revolution when working. I can't seem to get it to work, so I may not be able to do the visual on the other ones.
Okay.
Sorry about the short notice. So here's the one that you were just doing. And you can see that the intersection points are at x equals -3 and at x equals 2. So lovingly, GeoGebra has a nice command that just says the integral between two functions, and then I just have to give it a beginning and ending x value here, which is lovely. So I got 20.8 continuous 3.
Okay. And that's right, right? If I do 125 divided by 6, did anybody do that?
Sounds right, because 120 divided by 6 would be.
That's it. Yep. All right, we're good. Okay. Everybody didn't put Ashley, put your name in the chat. Jared, put your name in the chat. I'm glad to see you guys here. Glad to see y'all here. Okay. All right, Mr. Simon. Number 19.
Okay, so find the volume of the solid generated by revolving the region bounded by this graph and these lines around the line x equals 6. Be sure to graph the region and state what method. So, Vic, did you have a particular method in mind for
I do, because actually on the final this year, we do say what method. So let's use, for this one, let's say the shell method.
I was gonna ask if I could use the shell method.
Yeah, it's gonna be easier, the shell method. So let's go ahead and write in here, shell method.
Mm-hmm. Let's put it off to the right, or there you go. Okay. And do you have another one where they'll be doing discs and washers?
Yeah, the next one, yeah.
Okay. Cool. So I always start these out. These are very visual problems. You know, they really do need that extra little bit of visualization, just so that you can make sure and get the right idea about what you are doing. So I'm going to start by graphing the function, of course. The y equals x squared plus 1 being the parabola that goes through the point at 1 here on the y-axis. And of course, just being, other than that, just being the normal y equals x squared parabola. Okay, so then from 1 to 2 on the x-axis, so 1 and 2 being here and here, let's say, we're interested in this region here, right? Between y equals 0, which is the x-axis, right? That's here. So we're interested in that region there underneath the curve, but above the axis. But then much further down the line, we need to look at the line x equals 6. So I'll put that over here. Right there. Okay. So then if we're going to do the shell method, remember what that means is we're basically peeling layers of the onion and just doing the volume of individual little slices of layers, and it will grow either inward or outward from the center. Okay, so I'm going to just draw in a generic shell. The shell is going to be here, and it's going to rotate around the line that we're saying is the line of rotation there, like that, such that the radius of the rotation is going to be to that point. Or I could also have drawn it, you know, here at the bottom. Either way, it doesn't really matter. And I know I'm a little lopsided there, but you get the idea. So imagine those shells just, you know, growing in and out, being a bunch of the cylindrical layers there for that. So then I'm going to want to set up my integral here. Remember the formula for this, because I'm basically just doing the area of one of these shells, and the area of the surface of a cylinder, not the top and bottom, but the side of a cylinder, would be the 2 pi r, which is the circumference, right? And then times the height. That's the height being, you know, this thing right here. So basically all I need is to represent the radius and the height as some sort of function of whatever differential I'm using. So I'm either using dx as my differential or dy as my differential. Notice the way that I've sliced the edge over here. So you can notice the slice there has a thickness of dx, and I'm going to be moving it along the region from x equals 1 to x equals 2. So since my thickness there is a dx thickness, then I would like to have r and h eventually as some sort of function of x. And therefore, that's what will begin the setup of our integral. The volume is going to be 2 pi integral. I know I'm going from x equals 1 to x equals 2. And I need something representing the r, and I need something representing the h dx. Okay, so notice where r is. R is up here. Okay, now the distance from here to here is always 6 because we're just going from x equals 0 to x equals 6. Okay, the value of where I've sliced here is our current x value. And so the distance from here to here is always x. You know, whatever generic x we've picked, that's the distance that is. Our radius is the leftover bit from here to here. This is our radius right here every time. So every time we move x over, the radius is going to get a little smaller or a little bigger depending. But since I'm counting from 1 to 2, as I count, the radius is going to get smaller and smaller as I go. Notice the r is always going to be equal to whatever 6 was, take away whatever my x value was. So 6 minus x represents the radial value there. And then notice the height is going to be from the x-axis up to the function. That's my height right there, right? My height is basically my function of x. Well, we already know what that is. That's x squared plus 1. So I have my 2 pi times radius times height, which represents the area of that one shell that I've generically chosen. And then I'll be doing that along all of the x values from 1 to 2, and that will generate the volume that is being revolved around there. Okay, so let's go ahead and work that integral. I have 2 pi integral from 1 to 2. And I'm just going to FOIL that out and do some power rules, right? That's going to be 6x squared plus 6, and then minus x cubed minus x dx. No like terms there, so I'll just go ahead and do all of my rules here. Whoops, forgot my 2 pi. Squeeze that little 2 pi in right there. 2 pi times, this is going to be 2x cubed plus 6x minus 1/4 x to the 4th minus 1/2 x squared. And it's going from 1 to 2. So now we have nothing left but the arithmetic. So 2 pi times, when I plug in 2, I have 2 times 8, so I have 16. 6 times 2, so plus 12. And then 2 to the 4th is again 16, but divided by 4. So minus 4. And 2 squared is 4, but times a half, so minus 2. Minus, if I plug in 1, so that's just going to be 2 plus 6 minus 1/4 and minus 1/2 right there. Okay. So let's see. 16 and 12, that's going to give me 28 minus 6. This is 22 here altogether. And then over here, I've got a minus just these two pieces right here. I'll go ahead and subtract another 8 from that. So let's see, the 22 minus 8. So far, I've got 2 pi times, hang on, 14, right? 22 minus 8. And then minus 1/4 minus 1/2. What I'm going to do is I'm going to pull a 1/4 out of everything here. So I'll have 2 pi over 4.
I think we might have, I have something a little different before we go further, Dave. See how you have a minus in front of the minus 1/4?
Yeah. Did I miss something?
Yeah.
It should be negative x cubed, right? Because of the
Yeah,
x.
no, I think it should be a plus on your last step. It should be a plus 1/4 and plus 1/2, right?
Oh, thank you. Yes,
Okay.
because of the
Now
double.
we're on, yeah.
Drop the negative.
Everything else was good. It's just these little calculations
Yeah.
here.
Perfect. You caught me. Pants are down. Sorry. Okay, so factored out a 1/4. 14 times 4 is the 56. And then plus 1 plus 2. And then, of course, the 2 over 4 is going to reduce. That's going to give me, let's see, 59 pi over 2.
Yeah, now we're matched.
Yay.
Yay.
I squeezed it all in one space.
Okay. Any questions? I just want to let my students, just for clarification, where Mr. Simon has R, I put a P just to follow the textbook that we're using. But it's actually same exact method. So just I use 2 pi pH. So it just, his R is what we called P, but it's exactly the same way we calculated it. So nothing else is different, just a little notation glitch. And you have to be able to understand that, because when you're looking at other resources, I mean, they might not even call it R. They might call it, something else. So,
Well, and because I very rarely memorize things from textbooks or even use notation from textbooks because I'm horrible at memorizing. I
yeah,
always, like you notice I had to rebuild it like as I was
yeah,
going. I'm horrible at memorizing, but it makes sense to me if I do it from, oh, this is a cylinder. Let me do the area of
exactly.
a cylinder.
I get it. You derive the formula right on the spot.
Yeah,
Yeah.
I
And
can't.
so we tend to do that. Students tend to like to memorize stuff.
Yeah.
So I just wanted to call out that, we did use a P in class. So, but everything's
Silly letters. How dare they?
I know. We just need to know whatever it's the distance from the rectangle to the axis of revolution times the height of the rectangle. That's what you have to know there.
Right.
And that's in words. That's that's not even using any letters. That's just, the words. Okay, I'm clipping it now. Copy.
Now I might be able to, let's see.
If you got this on, okay, I'm ready to delete.
Oh, are you? Okay, clear. There is a website that has some of these things already built. I just always try to use my own stuff,
Mm-hmm.
but I'm looking at one of the websites right now to see if I can do this. X squared plus 1. And from A equals 1 to 2.
And do we have any questions while Mr. Simon is doing that? Does anybody have any questions about it? This is what we're doing this week. So you guys are, it's good of you to come in.
I'm good, thank you.
I chose 4 problems because that's what you have on the final. So you have four problems: an area, 2 volumes, and it does say which method to use on the final. So that's a little bit of, a little bit of guidance, to help you out. Earlier finals, previous semester's finals, didn't say what method to use. So it's a little bit more guidance for you guys.
Let's see.
And this one too. And this one we're going to use the disc washer on this next one. So you guys can get started on this one while Mr. Simon is pulling up GeoGebra for us.
Yeah, the only ones that they're doing are rotating it around the axes.
Okay. You want me to just go ahead and do this problem and you can?
Yeah, just keep going.
Okay.
That
Alrighty, guys.
That one's around an axis. I can possibly.
Yeah, this is on the x-axis.
Mm-hmm.
Okay. So and this one says find the volume of the solid generated by revolving the region bounded by the graphs of x squared and 6x minus x squared. So we have 2 parabolas, 2 intersecting parabolas, and we're going to revolve it around the x-axis. Be sure to graph the region and use the disc washer method to find the volume. So here we are using a different method. So let's look and see what this one entails. Okay. So the first thing I'm going to do is I'm going to find the intersecting points. Because this one doesn't give us, this other volume problem, it told us between x equal 1 and x equal 2, like it told us. Here, we're going to have to intersect these 2 curves, okay? So I'm going to get 2x squared minus 6x equals to 0. I'm going to factor out a 2x, and I get x equals 0, x equals 3. X equals 0 gives me the point 0, 0. X equals 3 gives me the point 3, 9. Okay. All right, one parabola opens up, the other one opens down. Let's go ahead and graph them. And I could have kind of offset it here a little bit, because it needs to go all the way up to 9. So I'm just going to call this 9, and I'm going to just call this 3. So 0, 0, and 3, 9. Okay, so let's the x squared, let's call this one the x squared. And then the other one, let's put that one in green. It just, this is the negative x squared plus 6x. Okay, so I have this, this area in here. And we want to revolve it around, what did we say? The x-axis. Okay, everybody with me so far? Any questions so far? So I graphed my region. I'm not going to show I'm not very good artistically, but I think you can visualize it, what's going to happen when we rotate it. The disc washer method uses a large outside radius, inside radius. You can say big R and a little r. And I'm going to see that I do have a little r. Little r is not always 0. There's going to be a kind of a hole in the middle, okay, as I revolve it. All right, let's draw my rectangle. I'm going to ask for some volunteer. Is my rectangle horizontal or is my rectangle vertical?
Vertical.
It is vertical. And how do you know? Who said that?
Because
Hi.
it revolves around the x-axis. That's why.
No, it's not really why. What method? It depends on what method I'm using.
Oh, what method are you using? You're using
Disc.
the disc?
Yes. Exactly.
And then
If I was using the shell method, my rectangle would be parallel, would be horizontal. Okay, so it's very important. You will always be given what axis or what line to revolve it around. And so because I'm revolving around a horizontal line, the disc washer method makes my rectangle vertical. Okay, so let me draw my rectangle. Let me use a different color. Let's use purple or something. Because I have a vertical rectangle, my width is delta x, so I know my integral is in x. So before I can't write my formula until I know that. Because when I write my formula, I'm going to write it in, I'm going to have a dy integral or a dx integral. So now I know I have a dx integral. So all these things, there's a logical progression of steps that you guys need to be aware of. Okay, because I have students asking me, Ms. Flanders, why do you have a vertical rectangle? Well, I'm told to use a disc washer method, and my axis of rotation, axis of revolution is horizontal. Because they're perpendicular means I need a vertical rectangle. Okay, so my formula is just pi, the integral from a to b, big R squared minus little r squared dx. Okay, let's find this big R and little r. Big R is the longest distance. Your rectangle is from the axis. This is big R. Well, that happens to be the parabola. The parabola opens upside down, or opens down. That happens to be that y value. And that y value is negative x squared plus 6x. Little r is the shortest distance. Your rectangle is to the axis. Okay? So that happens to be the blue function, the parabola that opens up. That happens to be x squared. Okay, I'm going to stop there. Do I have any questions? So big R is called the outside radius. Okay, it's the when you draw your rectangle, it's not always the top of the rectangle. Okay, so it's just whatever, the top or the bottom, whichever's furthest from the axis of revolution. And the little r is the closest distance your rectangle is to the axis of revolution. Okay, so over here, any questions, guys?
No, Miss Flanders.
Okay, so I have the integral from 0 to 3. Big R is negative x squared plus 6x quantity squared minus x squared squared. Did anybody want to say something?
Mm-mm.
Okay, so I'm going to square this out in my head here. You guys might have to do off to the side. But x to the 4th minus 12x cubed plus 36x squared minus x to the 4th power dx. And I see that these x to the 4ths, that's nice. Two terms that I don't have to use. So now I'm going to get, I'm going to integrate negative 12x to the 4 over 4 plus 36x cubed over 3. from 0 to 3. And I'm noticing, let's see, 4 goes into 12 3 times, and 3 goes into 36 12 times. I'm going to get here pi times -3 times 3 to the 4th plus 12 times 3 cubed. And I noticed that when I plug in 0, I'm going to get 0 both times. I'm just going to kind of take a little shortcut there. All right. 3 to the 5th power is basically what I have. So I have -243. 12 times 27 gives me 324. So I get 324 minus 243. I get 81 pi. And this is cubic units. And I don't think we put our units over here. You don't have to, but I'm just going to kind of, you know, this is cubic units. And this one is, I'm sorry. Yeah, that's right. This 125, this is area. So this one is square units. Okay. So 81 pi cubic units. Any questions?
I think I have something for you for the last one that I just did too.
Okay. And I do want to give you guys a heads up that on the final, you don't actually have to go through and compute. You just have to simplify the integral. So just set it up. So it's very important you can set it up. So you guys see us making little mistakes on those calculations at the end, and that's okay. I know you know how to do that. So it's a matter of what you're really learning here is to set it up. So pay close attention to that. Okay. All right, Dave, you want to go ahead and do your GeoGebra?
Yeah, let me grab that. So this is not perfect, but this is a different one that I had made that seems to be working pretty well. So here's the one that I did a minute ago, where we have y equals x squared plus 1. And we're supposed to be taking the section beneath it, or between it and the x-axis, between 1 and 2. So that's this region right here, as you can see. And we want to rotate it around x equals 6. So when we rotate that around, remember we're doing this by shells. So if you want to think of it this way, here's an individual shell. All right, now not the bottom and the top, but think of the side here. Okay, the side segment has the height that's with the function, and you can see the radius of the cylinder goes to the line there. So we just have a succession of cylinders, and when we're integrating, all we're doing is we're adding up all of these cylinders. This thing's not moving very fast. See all of the cylinders as this thing goes. If you think of adding up all of those little surfaces the whole way across, right? Then eventually what happens is you get a solid that looks kind of like this, where it has the slanted parabolic sides all the way to the edge. Then the bottom is kind of like a cylinder, but it's only as thick as this 1 to 2 ring here, because it's revolved around that thing right there. So it looks like that. And we're just doing it by those cylindrical shells there. Now I know you didn't do the last one by shells, Vicky, but I think in a second, give me a second to work on it. I can get this one to look like that last one you just did too.
Okay. Do you want to work the last problem? Or do you want to wait? We have.
Yeah, I can work the
minutes.
next one if you want instead.
Okay. Or, I mean, you can, whatever you want to do. If you want, I don't know how long it's going to take you to pull it up on GeoGebra.
I mean, it's the same program. I'm gonna use this. I'm just gonna change the functions to match what you did there. 6x minus x squared Okay, and we're just revolving it around the x-axis.
The x-axis, yeah.
Oh, yeah, that's going to be a problem. This one was set up to do vertical integrations.
Yeah.
This one that I just did was set
Oh.
up for that, but it's between. Oh, yeah. Let me try my old one real quick. Okay, so here, let me
Okay.
start over. Oh, yeah, so I did get some of it here. Let me show you what it looks like. Sorry, I just restarted the recording there. So yeah, like as I was saying a second ago, you can see the idea of this thing because the top of it, the outside of the integral is the larger portion, the outside here. And then as you're integrating, the way that you're going to see this is by seeing what the washers look like, right? So as I can zoom in a little there, you can see as it gets to the outer edge there, it gets real thin. So it's not a solid volume. It's this piece right here being rotated around, if that makes sense.
Yeah.
Okay. So yeah, let me go ahead and do that next one.
Yeah, and it's not hard. You can do a visual on that one, but you don't have to graph it first. It's just an arc length.
Oh, is it an arc length?
Yeah, it's an arc length.
Oh.
So on arc length, you don't have an area or a rectangle.
You don't have a 3D.
You don't have, yeah. So you just
What about a surface
and
of evolution?
I don't have that on here.
Oh. Yeah, okay. Go ahead and share screen and get.
Oh yeah, sorry about that. Already have it set up here.
Okay. And it's going from 0 to pi over 4?
Yeah. So do part C.
Okay. 1 second. I was actually pulling the graph up there.
So I did, just to kind of some clarification, give you guys a heads up. I did say that you wouldn't have to do these applications of the integral. All of these, you just have to set them up. But whenever you set them up, you need to simplify the integrand as far as you can. So in other words, get it to where you would integrate, just don't integrate. Okay. So in other words, don't just stick what you have in the formula. You got to simplify that integrand. So simplify that formula all the way down. But we're going to work it out all the way. I just want you to know how far you have to go on your
Work it
exam.
as far as we can until we can't.
Yeah, and then we're going to work it all the way out because it does say find the length.
Okay, so the only problem with that, Vicki, is that it's very easy to get elliptic integrals from these that can't be that have no closed form. So hopefully this is not one of those.
No, it's not. It's not. We're not going to give them nothing like that.
Okay.
Also, sometimes, let me just say one more thing, Dave, before you get started. Sometimes I've had students that they don't even know what to do in this problem because it doesn't say arc length. Okay, so arc length is the length of a curve. The length of you can have a straight line and find the length as well. So the length of the graph, that it means arc length. Okay, so but I had students that have no idea like what to do in this problem. So just the terminology. Okay, go ahead. Sorry.
No problem. Okay, so I've already written the formula there.
Yep.
And so what I need is I need the derivative. Since the derivative of ln is 1 over, right? So 1 over whatever's there, then chain rule times the derivative of the inside would be negative sine. So it looks like my derivative is just the negative tangent of x.
Yep.
Okay. So then I'm going to plug this in to there, obviously. And I'm going from 0 to pi over 4. So my length is going to be the integral from 0 to pi over 4 of the square root of 1 plus, and when I square, the negative is going to go away. So I'm just going to say tangent squared, right, dx. Next, I'm going to have to simplify the inside there. I'm just going to remember my old Pythagorean identity, my buddy. 1 plus tangent squared is equal to secant squared. And right here, I got to be a little careful because the square root of something squared technically should be the absolute value of that object. From 0 to pi over 4, though, that's all quadrant 1. And nowhere in between 0 to pi over 4 is secant undefined. I have a constant stretch there of secant where it's not bouncing like between the up u or the down u of its own self. So I actually can just say, oh, well, the absolute value is the same value because it's positive. Luckily for us, because it's 0 to pi over 4, we can just say, oh, okay. If that wasn't true, then I would have to split my integral into several pieces and then only integrate sections that were all of the same quote unquote type. But here we have all positive, so I can just drop the absolute value. And then the antiderivative of secant. Anybody remember that one?
I'm waiting for somebody to say something. This is one of your integral rules.
Yeah, it's one of the more obscure ones.
Yeah, so we don't use it that often, but it is. You do need to know them all. Know them all for the final exam.
Anybody know this antiderivative?
If I start off natural log,
Yeah, it is ln of the absolute value of secant plus tangent. Oh yeah, that's the one. That's right. 0 to pi over 4. Okay. So plug in pi over 4. Secant of pi over 4 is the square root of 2. Tangent of pi over 4 is 1. Minus secant of 0 is 1. And tangent of 0 is 0. The natural log of 1 is also 0. So this is gone. Therefore, I'll write it again just to be a little bit prettier. 1 plus square root of 2 here.
So I noticed it looks like Mr. Simon just dropped that absolute value, but he did not just drop it. He calculated it exactly. He calculated it, and sometimes we do that. You know, well, you have to do that, but sometimes you could do it in a different step. But you guys realize that square root of 2 plus 1 is positive, so you just can drop the absolute value. Not drop it, but calculate it.
This whole thing is 0.8814-ish.
Okay, units. And these are just units.
Yep, just units.
Because it's just a length.
Mm-hmm.
All righty, guys. Any questions? Just make sure you know your formulas.
You want to see the
Yeah, let me clip this.
Go ahead and clip it.
Yeah, let's see. Okay. Got it.
Okay. Okay, so this function, the ln of cosine of x, looks like this crazy looking guy. Notice there are sections of it where the function just flat out doesn't exist. That's anywhere cosine is 0 or negative, because the logarithm can't handle a 0 or negative input. So then what I'm getting here is just the regions where cosine is positive. The ln of it gives you one of these values. Now, we are only interested in the length of this thing from 0 to pi over 4. So I'm going to create another function here so that you can see that gap. Y equals if 0 less than x less than pi over 4. then you can be F. Okay, so now I've got a function that just represents a small part. Do you see the small part here when I?
Yeah.
So really what we're doing here is just finding the length of this little piece here, right? And I can do the length of a function here, F. Start x value 0, end x value pi over 4. And that's what we came up with, the 0.8813, like that.
Nice.
Yeah, it's pretty cool.
Yeah. Alrighty. And that was just about an hour. a little
Yep.
over, but we started probably a little bit 3 minutes or so later. So
I'm
that
going to
was
say
good.
thanks for coming because I'm turning off the recording here.